We finally are going to jump into learning about the chemical reactivity of organic compounds. You've learned about how inorganic compounds react in Gen Chem, and we've learned the proton transfer reaction for organic molecules. But now we are ready to get into all the different types of patterns of chemical reactivity. Now, not all of them, but many, and it's really exciting. So in this video, I'm going to teach you frontier molecular orbital theory. This is a predictive tool that we'll use to predict what in the world is going to happen when you combine two molecules together. And then there will be some patterns. And we're going to start to look at those patterns of chemical reactivity, but we're really going to take them step by step in detail later. Okay, so a bunch of goals here, a lot. Many of these you have, a few of these you've already met. You can probably already identify HOMO and LUMO and predict whether or not a species will behave as an electrophile or a nucleophile. So electrophiles are electron poor, nucleophiles are electron rich. We often abbreviate nucleophile as Nu- and electrophile as E+. We will then start to think about what the different elementary steps are in organic chemistry, and we're going to actually predict when they occur using FMO theory, and that's going to be pretty exciting. And then you're going to want to recognize those 8 steps. And what I mean by that is if I were to write down this equation to you, this is an inorganic reaction. Oops. All right, it's still a little early in the morning here for me. If I was to write this down and ask you what type of reaction it was, or not even give you the products, you would see that you have two aqueous salts, and you say, oh, this is the double displacement. There could be a precipitation. I need to check and see whether or not any of these compounds is insoluble in water. Calcium carbonate is, so that will be the precipitate. Okay, so this is the inorganic chemistry equivalent of what we're doing today. Except I'd argue what we're doing today is a little bit more complex. All right, so there are many patterns in chemical reactivity. We're going to learn this one overarching method of predicting reactivity. So that is FMO theory. And then we're going to take the patterns, and these patterns, that's like for inorganic chemistry, that's double displacement, single replacement, combustion. We're going to learn them one at a time later in detail. We're going to start to learn to recognize them today. Let's start with FMO theory. So let's imagine that we mix together molecules A and B, and they generate C and D. Now, what happens when we do that? Well, of course, we're going to break bonds in A and B and make some bonds to end up with C and D. Now, if we want to think more deeply about what happens, it involves electrons, right? All chemistry is about electrons. And so frontier molecular orbital theory, or FMO theory, helps us consider what's going on with the electrons. So the electrons are in orbitals, and molecules A and B have many different orbitals and lots of different electrons. So what do you think happens when A and B approach each other in space, when they collide in the proper orientation for a reaction to occur? Well, all of their orbitals overlap, okay? Every single one of their orbitals overlap. So all of these orbitals with A overlap with all of the orbitals in B. And that's pretty complicated, right? We have to think about all the different interactions. I can't even draw them all, but all the different orbitals overlap. Okay. Now, that's a lot to consider. So let's think about whether or not we can pare down or focus on certain interactions. So there will be 3 basic types of interactions between molecules A and B, depending on whether or not the molecules are filled or unfilled. So let's imagine that we have a filled orbital on A, and let's use this one for fun, interacting with a filled orbital in B. Let's go ahead and look what happens. So we take 2 orbitals. The one for A is on the left, B is on the right. We combine those two orbitals, and you know you'll make two new orbitals, right? When you mix two, you make two. Okay, so these are the new orbitals that we've made in the middle. Two electrons go in the lower energy orbital, two electrons go in the higher energy orbital. So what has happened? Well, nothing really. Two of the electrons, these two, they're lower energy. These two are higher though. So there's no net stabilization of electrons. Thus, we don't care. We can ignore this interaction. Super, so that means we can ignore all of these interactions between all of these orbitals of A and B. That's a lot that we can rule out now. All right, so all of these that I'm drawing, yeah, that's super fun. We can ignore all of them. Awesome. Let's move on to the next type of interaction. Let's take an unfilled orbital on A, let's take this one, and interact it with an unfilled orbital on B, and think about what happens. So again, here's our orbital from A, here's our orbital from B. They're closer together in energy this time. So they're closer together in energy, so that means our new orbitals will be lowered more and raised more, because we'll have better overlap between the two orbitals we started with. Okay, now what? So we made our two new orbitals. One is lower energy, one is higher energy than where we started. Oh, but there's no electrons. So what do you think? So there's no electrons to stabilize here, meaning there's no electrons to put in the lower energy orbital. So you guessed it, we don't care about this interaction, or we can ignore it. So much more fun to use unkind words. All right, last option here. So the filled orbital with an unfilled orbital. So let's look at this orbital on A. It's filled. And we'll just keep looking at this orbital on B, which is unfilled. And let's think about what happens. So here's our orbital from A. Here's our orbital from B. The electrons had the orbital from A had electrons in it. We generate two new orbitals. One is lower energy and one is higher energy than where we started. And then these electrons, they're going to go in the lowest energy orbital. So what have we seen here? Aha, electrons have been stabilized. So this is the interaction that we care about. And they've been stabilized by this difference in energy. So this is awesome. This is the interaction we care about. So we care about the filled, unfilled interactions. So instead of having to worry about all the orbitals overlapping, because all the orbitals in reality, they all overlap. So instead of having to worry about that, we can just limit our focus to the interactions between filled and unfilled orbitals. Still a lot of interactions, maybe we can limit it some more, but that's where we are right now. So it turns out that interactions between orbitals that are close in energy are more significant than interactions between orbitals that are further apart in energy. This is the case because we will have better overlap, meaning the MOs that are formed from those two orbitals coming together, they will be lower energy when the orbitals that we start with are closer in energy. Lots and lots of words. Let's diagram it. So if we start with two orbitals that are close in energy, I gave them pretty similar energy. They overlap in space and they form two new molecular orbitals. One is much lower in energy, one is much higher in energy by about the same difference in energy. Now, if we start out with two orbitals that are further apart in energy, we are going to get two new orbitals, but one of them is lowered, not very much compared to where we started, right? That's not a very significant difference in energy, especially not compared to this one. And then the other orbital is higher in energy than where we started. So when we start out with the two orbitals close in energy, we get a big stabilization in the new MO. So the new molecular orbital is significantly lower in energy, which is just not the case when you start out with a bigger difference. In this case, energy difference is big, and we get a smaller stabilization in that molecular orbital. So that's really good news for us. That means that we can just limit our discussion to orbitals, filled and empty orbitals that are close together in energy. So that means that we're only going to need to consider the frontier molecular orbitals, hence frontier molecular orbital theory. You've already actually thought about the frontier molecular orbitals. So we have the HOMO, the highest energy occupied molecular orbital. This has electrons in it. Will be our filled orbital that we were discussing earlier. And then the lowest energy unoccupied molecular orbital. This has no electrons in it, and that will be filling the role of our unfilled orbital that we discussed earlier. So this would be the HOMO, the filled orbital, and the empty orbital, the LUMO. Okay, so for molecule A, this is the HOMO. For molecule B, this is the HOMO, the highest energy filled molecular orbital. For molecule A, this is the LUMO. For molecule B, that is the LUMO. So what that means is that we only have to consider what this all means, this interaction and this interaction. So we've cut down having to think about, all of these, and I didn't even draw them all the interactions between the orbitals. We said, no, wait, only the filled, unfilled are important. And then we could narrow it down again by saying, okay, well, we get the best overlap when orbitals are close in energy. So then in that case, we don't have to worry about how this orbital interacts with this one because they're far apart. All we need to worry about is how it interacts with this one, the lowest energy empty orbital. So we're in really good shape now. So now we've narrowed our analysis down to two interactions. And typically the more significant one of those two combinations will have the lowest energy difference. So for A and B, it looks like, man, we're going to have a lot of colors of highlighting. This difference in energy is smaller. And so it would be the interaction that predominates. But we're not supercomputers, so this is kind of hard to know. So once again, we can show the interactions between the HOMOs and LUMOs of molecules A and B. These interactions are the single most important interaction for these species because the difference in energy between these orbitals is the smallest. And of course, one of the orbitals is filled. That's the HOMO. And the other is unfilled. That's the LUMO. And so because of that, we will have net stabilization of electrons. And then, of course, for these particular species, the difference in energy between the HOMO of A and the LUMO of B, that is smaller than the difference in energy between the LUMO of A and the HOMO of B. So it will just be this interaction that is significant. All right, that's a lot of theory. Let's take a minute and think about the order of the energies of molecular orbitals for organic compounds. So we can make some generalizations about HOMOs and LUMOs so that when I draw this molecule and I ask you, what's the HOMO, that you don't have to think for 15 minutes, that you can just make some quick generalizations, quick predictions. So the lowest energy molecular orbital is the sigma, and then the pi, and then non-bonding, and then pi star, and then sigma star. And then, of course, within every group of orbitals, the ones derived from more electronegative atoms will be lower energy. So the lowest energy type of sigma might be, say, sigma CX, and then, say, sigma CC, and then sigma CH, right? Where X is some electronegative atom. So within each group, orbitals derived from electronegative atoms will be lower energy. So we can see that within the pi group. We can see that within the non-bonding. X will have lower energy orbitals than C. X is more electronegative than carbon. Pi star CX, lower energy than pi star CC. And then finally, sigma star CX, sigma star CC, and then sigma star CH at the top. Okay, so now if we want to think about which of these orbitals can be typical HOMOs and LUMOs, we have to think about which ones are filled and empty. Now typically, all of these are going to be filled. So sigma orbitals, pi orbitals, those bonding orbitals, they're filled. So the filled orbitals might be able to serve as the HOMO, the filled orbital. We're going to refer to these as donor orbitals because they'll be donating the electrons that are in them. Now, carbon is a little bit tricky because it could be empty or filled, the non-bonding orbital on carbon. So you can imagine that you have an empty orbital on carbon or you had a carbon ion. So that's a little bit tricky. And so it could be HOMO or LUMO. And then let's look at these. These are typically empty. The antibonding orbitals are typically empty. And so the empty orbitals, those could serve as our LUMO or acceptor orbitals. We will fill them up with electrons because they are empty. So we're going to list our best HOMOs and best LUMOs. Let's go ahead and start with the HOMO, the donor orbitals. And the color coding is going to be a little bit weird here, so we'll talk about the best donor orbitals. The very best one will be the highest energy one. Okay, so if there is a lone pair, if we have a carbon ion, if there is a lone pair in this carbon non-bonding, this would be the highest energy of the filled orbitals, right? So that would be our best donor. And then an electron pair on X, that would be our second best. It's almost as high energy as a carbon ion. And then finally, our third best, this would be pi CC. Okay, so I'm looking at high energy, so up here, filled orbitals. The highest, the best, would be the carbon ion, then a lone pair on X, be that oxygen, whatever, lone pair on X, some heteroatom, and then finally pi CC. Everything else is usually too low energy to get involved. Usually, there are not many always statements here. All right, now let's take a look at potential acceptor orbitals. So the best acceptor orbital will be the lowest energy. So that would be the lowest energy empty orbital. That would be carbon if it's empty, if it's a carbocation. That would be our lowest energy empty orbital. And then pi star CX, that would be our second best. I have to tell you, typically pi star CC is not a good LUMO, but we'll talk more about that as we continue in the class. And it turns out that sigma star CX, this is our next best LUMO. And then it just gets too high energy up here. All right. So you want to keep this in mind. You should really, that this is a really important slide here. So you want to keep in mind the relative energies of the orbitals, which orbitals are usually filled and empty, and then what orbitals are typically the highest energy filled ones. So highest energy filled carbon ion, then lone pairs on some heteroatom, then pi CC. Those are all good donors. Good acceptors, well, if we have a carbocation, if we have a pi CX, the pi star orbital is a good acceptor, or sigma star CX. You really want to keep this in front of your brain. All right, so using this chart, I want you to practice finding the HOMOs and LUMOs for these molecules. So please pause and try that. So you can do this the easy way or the hard way. The easy way is to have this chart in your mind and ask yourself, all right, well, does the molecule have a carbon ion? Does it have a heteroatom with a lone pair? Does it have pi CC? The hard way is to draw the entire FMO diagram out and then from there, identify HOMO and LUMO. So I've kind of given you an example of the hard way and the easy way down here. I did forget to fill in my electrons. So for ethyl bromide, this first molecule that we're looking at, I mean, you could make an FMO diagram, and then you would see, oh, the highest energy filled orbital is the non-bonding orbital on bromine, and the lowest energy empty orbital, that's sigma star CBr. Or you could just have this in mind and say, all right, it doesn't have a carbanion, but it does have these lone pairs on bromine. So that's the HOMO. So, I think it is much, much, much easier to have this chart in your mind, right, than it is to draw a full MO diagram. So let's try for the ketone. So for the ketone, there is no carbanion, but there are lone pairs on oxygen. So the non-bonding electrons on oxygen, that is our HOMO. The LUMO, well, there is no carbocation, but there is a pi star CO in that double bond. So that's our LUMO. For the alkene, there is no carbanion, there is no heteroatom, but there is a pi CC. And then the LUMO would be pi star CC. Now, of course, I mentioned pi star CC is not a great LUMO. So what would that tell you? That would just tell you maybe it's not going to react. And that's useful information. Okay, so you should be able to find the HOMO and LUMO of a molecule by looking at it. Again, the hard way, which you've already done, is drawing complete MO diagrams. Easy way is to keep this in mind. Now, we still need to be able to draw the cartoon molecular orbitals because the shape of the orbitals matter, overlap matters. It really, the shape of the orbitals will determine whether or not they can overlap, whether or not a given HOMO-LUMO interaction overlaps, and then how they overlap. So pause and please try to, first name the HOMO or LUMO of each of these molecules. And you might have to draw them out, and then draw the picture. Please try this. It's really important you try yourself. Okay, now that you've tried that, let's take a look at the answers. I'm not gonna actually explain all of these, so I'll just pause long enough for you to look at them. The one that I will point out is pi star CO, and this might be new to you. I drew pi star CO a little bit bigger on carbon, and that's because antibonding orbitals have a larger coefficient, or are bigger, on the less electronegative atom. So they're bigger on the less electronegative atom. And so let's think about it. So I have this, let's zoom in. So carbon and oxygen, they're different in energy. Oxygen has lower energy orbitals. So when they make two orbitals, the bonding is actually closer in energy to oxygen. So it'll be bigger on oxygen. The antibonding is closer in energy to carbon, and so it's bigger, has a larger coefficient on carbon. All right. So now these molecules have several or more than one possible HOMO and more than one possible LUMO. And I bring this up because life is chiral, life is also complicated. We often will have to consider multiple reactive sites. Now, you're probably thinking, no, there is one absolute lowest energy empty orbital. Yeah, you're right. But if two of them, so if you have two empty orbitals, that are kind of close in energy. I mean, if they're close enough and you're at room temperature, like both of them can probably react. So we need to be able to identify all the possible reasonable HOMOs and LUMOs. And how do you know what's reasonable? I've told you. It's these orbitals. These are the reasonable ones. So if we want, we can just copy and paste this. Those are the reasonable HOMOs and LUMOs. Put it over here this time. All right, so let's look for these two molecules. So we have an alkene and we have a ketone. We have an epoxide and we have an aldehyde. Let's do highest energy filled orbitals first. So we'll do HOMOs first, potential donors. So we have, for the molecule on the left, there are the lone pairs on oxygen. Those are certainly potential donor orbitals. And then you have your pi orbitals on the alkene. And so the pi CC is also a potential donor. So we had two potential donors here. All right. Okay, now for the LUMOs, that should be fun to draw them on the same molecule. For the LUMOs, we have pi star CC. Oops. And pi star CC is actually not typically a good acceptor. So probably not. And then we have pi star CO. Oh, this is a good acceptor. Pi star CO is a really good acceptor. Okay. So I would bet this would be the LUMO if this molecule reacts as an acceptor. That is an ugly pi star CO, but we're going to roll with it. All right, for the next molecule, HOMO, well, we have a bunch of lone pairs, right, on these oxygens. And then for LUMOs, well, we have a couple options. We still have pi star. I don't know why I'm drawing such ugly pi stars. We still have pi star CO as our LUMO. And whereas probably we didn't have to consider the pi star CC, I know you don't understand why. You have to take my word for it for now. We do need to consider sigma star CX, and we have that. We have a sigma star CX. We have two of them for the epoxide. We can put our phasing in, and then there's another one at the other carbon oxygen bond as well. But I don't want to draw it because it'll be truly messy. So we do have two potential LUMOs for this molecule. All right, so how will you know which one reacts? Well, that's like the subject of the rest of the year. So we'll get to it. For now, we're identifying them and recognizing that molecules can have more than one reactive site. Okay, we're finally ready to use this for something. So for both of these molecules, I want you to pause and identify the possible HOMOs and LUMOs. Select the likely nucleophile and electrophile. All right, what do nucleophiles do? Nucleophiles donate electrons. So what are they going to use? They're going to use the HOMO. Electrophiles, they accept electrons. They're going to use the LUMO. They're going to use that empty orbital to accept electrons. Then show how these species will react using curved arrows and predict the products of this single elementary step. Okay, pause, do it, force yourself. All right, so if we identify the HOMOs and LUMOs, the HOMO for hydroxide is the non-bonding pair of electrons on oxygen. And the LUMO, the lowest energy empty orbital, that's the only one that we have, sigma star OH. For methyl bromide, we have the non-bonding pair of electrons on bromine, and then sigma star CBr as our LUMO. Okay. So that was the first step. And if you have trouble doing that, remember you can do it the easy way or the hard way. And it's okay if you have to do it the hard way for a while. You can draw out the molecular orbital diagram just like we were doing weeks ago and identify the highest energy filled and the lowest energy empty orbitals. While you're doing that, try to commit these patterns here to memory so that you can just look, rather than having to write out the whole diagram. All right, so here we go. And then now we need to figure out which combination is it. Is it this HOMO-LUMO combination or is it this one? And here's another moment where our best HOMOs and LUMOs list comes in handy. So non-bonding oxygen, that would be here. That's a good HOMO. And then the sigma star CX, That would be a good LUMO. And so this is the combination that we will observe reacting. And you can try the other. So if you're still confused about why that is, try this. It's going to look crazy. Okay, so now we need to draw. So that means that if we're going to use the HOMO for hydroxide, then this is going to be the nucleophile, the electron-rich species. And you might say, of course it is. It has a negative charge. Okay, well, good. You're one step ahead of me. And then that means our alkyl halide here, that's going to be the electrophile. So nucleophiles donate electrons. So you're going to start your curved arrows at the nucleophile and you're going to point to where they're going. So they're going to sigma star CBr, which you know is bigger on carbon because carbon is the less electronegative atom. And we just discussed antibonding orbitals are bigger on the less electronegative atom. So when we fill an antibonding orbital, so we filled sigma star CBr, that breaks a bond. So filling sigma star CBr breaks sigma CBr. Another way to think about this is you can't violate the octet rule. Carbon can only make 4 bonds. And so if you're going to make a 5th one, that's not going to work, so you do need to break one. So we end up with methanol and bromide, where these electrons and the CBr bond are here on bromide. Excellent. So we know nothing about this, and we were able to predict this reaction between these two species, at least the first elementary step, just by using HOMO-LUMO analysis. Good job. So this reaction that we just predicted using FMO theory is an example of what's called a bimolecular nucleophilic substitution reaction. And we're going to go ahead and diagram this out a little bit. So I mentioned that we're going to learn FMO theory. That's our huge focus. If you can do this problem, awesome, awesome, awesome. This is our goal. And we're going to start to analyze these patterns. So after every time we predict a reaction, I'm going to then introduce the pattern to you. And this part we're going to keep working on this. So we're going to go into this reaction, the SN2, in detail later. But for now, there's a nucleophilic species, an electron-rich species, that reacts with an electrophile, an electron-poor species. And if you didn't really connect with that antibonding orbital is bigger on carbon than on bromine, well, you can also think about opposites attract, and there's certainly a partial positive on carbon, and so that can explain why the electrons attacked carbon. So the electrons attack sigma star, CBr, filling an antibonding orbital, breaks the bond, and then those electrons go with bromide. So we form a new bond, we form a new sigma bond, and then there's a new lone pair on bromide. So new sigma bond formed in the product. Well, this is called the substitution product, and that's because you have replaced bromine with hydroxide with the nucleophile, and then bromide, it left methyl bromide, so it's called the leaving group. All right, so we have a nucleophile and electrophile. We have a new sigma bond being formed and a group leaving. So we start out with 2 things, we get two new things. Let's look at the FMO analysis. So we have the non-bonding oxygen attacking sigma star CBr. Okay, so you have your orbitals nice and lined up here. So this is allowed. We have our orbitals nice and lined up, and they're interacting in the same phase. And again, filling sigma star breaks sigma. I'll write that down one more time. Okay, all right, let's go on to the next one. So let's use FMO theory to predict the reaction between these two species. So same steps. If you want to pause and try yourself, please go ahead and do that. Okay, so for chloride, I mean, this only has a HOMO, right? There's no empty, well, there are empty orbitals, but there's not an empty molecular orbital and certainly not one on our list. So that makes our life a lot easier. We're pretty sure this is going to be the nucleophile and it's going to react through its HOMO. Now for the terbutyl cation, which is what we have here, terbutyl cation, its HOMO would be, let's think, it would be sigma CH. That would be its highest energy filled molecular orbital. Now, this is not going to be reactive. That was not on our list. We can copy and paste our list. I don't see anything about sigma CH being a good donor. It's not. It's really low energy and it's not going to be a good donor. So in a way that's nice because that does confirm for us that we will have the HOMO of the chloride reacting with the LUMO, which is the empty p orbital on carbon here. Okay, so these two orbitals are going to come together. The terbutyl cation, that will be the electrophile. We want to draw the curved arrows. So start at the HOMO and point at the LUMO. So let's draw what we get. We get the species. All right, excellent. So we had a non-bonding HOMO come together with an empty non-bonding orbital, and we just formed a bond. So there's the bond that we formed. This is an example of a coordination reaction or coordination elementary step. So let's think about how we can generalize the pattern that is represented by this reaction. Well, first of all, we start out with two things, right? Two things, and we get one, so two become one. So two things came together to form a new sigma bond. This elementary step is an example of a Lewis base, which has an electron pair to donate, reacting with a Lewis acid, which has an empty orbital to accept electrons. So it's a classic Lewis base, Lewis acid reaction. It just forms a new sigma bond. Now we can look at the FMO analysis here, and we want to, let's scroll down. So we have that non-bonding pair of electrons on chlorine attacking or filling up that empty p orbital on carbon. So we have a donor to an acceptor. Excellent, and you were able to predict it having never ever even heard of this, right? You did this, you predicted it, never even hearing of a coordination reaction before. Now, let's talk about heterolysis. So this is the third of 8 elementary steps we're going to discuss today. Heterolysis is the microscopic reverse of a coordination step, which means it's the exact reverse. So let's map this out. So this one, what do you think? It's the reverse, so which means we're going to form the carbocation and chloride. So this sigma bond, it just breaks. So in a heterolysis, we will break the sigma bond. And we end up with, non-bonding pair of electrons and an empty orbital. All right, you might ask, why does this happen? Well, it does. As you know from learning about IR spectroscopy, all bonds are vibrating, and this bond can just vibrate so much, and usually can require some heat. So you have heat, and the bond just vibrates or stretches until it breaks. And it's going to form a carbocation, and it's going to form chloride. And of course, these species need to be low enough energy that this is okay. And we'll talk about it more later. Okay, but that's the heterolysis step. Now you see one thing becomes two. You just break a bond. It is the reverse of coordination. Let's predict another step. Yes. All right, we're going to use FMOs to predict the following reaction. Let's identify the homos and lumos of both species. Let's select the likely nucleophile and electrophile. And selecting the likely nucleophile and electrophile, it is from thinking about this, right? Thinking about what are the good homos and lumos. Well, and then you might be asking again, well, how do I know what the good homos and lumos are? Well, you trust me because I know a lot about chemical reactivity and I'm distilling it down for you. And you will learn more and you will understand more later. All right, so let's do this thing. So the HOMO for, pause if you want to try it on your own first. Okay, the HOMO for ethylene is pi cc and the LUMO is pi star cc. Do it the easy way, do it the hard way, it's up to you. The HOMO for HCl will be the non-bonding pair of electrons on chlorine, and then the sigma star HCl will be the LUMO. Now, we have to pick out which one is the nucleophile and which one is the electrophile, and that's kind of hard here, right? Because nucleophiles donate electrons. We often abbreviate it NU with a minus, but neither of these species are charged. And so it becomes really hard to predict which is the nucleophile and which is the electrophile. And that's where we really need to think about this list. So we have said that pi star is not a good acceptor, but pi is. Pi is on the list of potential homos. So I'm going to predict that the alkene here is going to react as a nucleophile. It's going to donate electrons. And that HCl is going to act as the acceptor. It's going to react through its LUMO. All right, so let's do it. Now you might say, well, okay, I can start the arrow, but then where do I point it to? Well, we can think about this in two ways. An antibonding orbital is bigger on the less electronegative atom, has a larger coefficient on the less electronegative atom. But you don't even have to do that, right? You can just remember that opposites attract, and there is a partial positive on hydrogen, and electrons are negatively charged. So opposites are going to attract here. You're going to fill up sigma star HCl, and that breaks sigma HCl. So filling sigma star breaks sigma, and that will end up giving us this species. So one of those carbons is going to make a bond to hydrogen, so we'll just make it this one, and then the other carbon is just going to have an empty orbital, and then you end up with chloride, where it has accepted the electrons from the HCl bond. So this is called an electrophilic addition step, where you've added an electrophile to a pi bond. So add an electrophile to a pi bond. So the alkene acts as the nucleophile. And you're going to add an electrophile to the alkene. Okay, so that's it. So you know the arrows for that. I'll just show you one more time. So this first arrow, and I think the first arrow can be confusing because only one of the carbons can bond to hydrogen. So one carbon of the alkene bonds to hydrogen. And then the other one, well, sorry, but it has an empty orbital now. And then we have chloride. And that's where these electrons and the HCl bond went. So just remember, fill an antibonding, break a bond. All right, so we'll talk more about this reaction type later, but for now, my big goal is that you could predict it using FMOs. So if you understood this slide, awesome. Cardy's goal in the textbook is that you start to recognize this pattern. We'll get there. So you're just going to start working on recognizing the pattern. Now, electrophile elimination, this is the reverse of electrophilic addition. just like we had coordination and heterolysis were microscopic reverses of one another. So in heterolysis, we just went backwards and it reformed these species. So coordination. Electrophile elimination is the reverse of electrophilic addition. So we're going to map this out. So we can already see what's happening. We don't actually, need to think too much because we've learned how to analyze curved arrows. So it looks like the electrons in that bond go here. It looks like this bond is broken. So sigma bond is broken. And then those electrons are used to form a pi bond. Because here's a proton without its electrons. So what we're going to have is we're going to have these electrons come down. And there we go. We're all done. This carbon always just had that one hydrogen, implied hydrogen on it. So this is considered an electrophile. So some sort of electrophile leaves and a pi bond is made. Okay, so that's how you can recognize electrophile addition. And again, it's the reverse of electrophilic addition. So for example, if we went in the reverse direction, we can imagine that pi bond accepting a electrophile. So this is certainly acting as a nucleophile because it donates electrons. This is certainly an electrophile because it accepts electrons. Okay, and it would give us what we started with. All right. So you just want to start to recognize these different reactions. We're doing awesome. We have learned 5 of the elementary steps, and we have predicted 3 of them. So we'll just do a little bit of a recap here. So we predicted bimolecular nucleophilic substitution. We predicted coordination. Awesome. And then once we learned coordination, we said, well, there's heterolysis, which is the reverse of coordination, which is a little bit harder to predict, but cool. We can see it's the reverse of coordination. Then you predicted electrophilic addition. Yes, awesome, good job. And then just like heterolysis was the reverse of coordination, we said, hey, well, the reverse of electrophile addition is electrophile elimination. And so we saw that. You can handle it. And now we're going to predict our 6th elementary step here. So this will be what? The 4th one we can predict based on FMO analysis. So here are 2 species. I want you to, again, identify possible homos and lumos, select the likely nucleophile and electrophile, and then show how these species react using curved arrows. So let's go ahead and do that together. Now, something that I did something a little bit tricky on purpose is that I put this species here. So let's write about it up top. This is called an organolithium species. It kind of has a carbon-lithium bond, but we know that bonding is not black and white. There's no such thing as purely ionic or purely covalent. Let's be honest, this is a mostly ionic bond with a little bit of covalent character. So we can really think about this species like this, and that might help us with our HOMO-LUMO analysis. Okay, so let's take a look. So the highest energy filled molecular orbital for this species, I would accept 2 answers. I would accept non-bonding electrons on carbon if you were thinking about the ionic kind of picture, or I would accept sigma electrons in this carbon-lithium bond. We're talking about the same thing here. So either way, we're good. All right, so the luma would be sigma star Cc. Now let's look for this acid chloride. we have an acid chloride reacting with an organolithium reagent, so organometallic reagent. So the HOMO of the acid chloride, this will be the non-bonding electrons on oxygen. Because chlorine is more electronegative, so its lone pairs will be lower energy. We want the highest energy filled molecular orbital. The LUMO is going to be pi star CO. All right, what do we think happens here? Well, pi CC, not really a LUMO, not a good acceptor. So I'm pretty sure is going to be the highest energy filled orbital for the organometallic reagent reacting with the LUMO of the acid chloride. Right, this looks, I mean, the organolithium reagent, it looks really electron rich, doesn't it? Really electron rich. Thus, I bet this is a nucleophile. So it's going to use its highest energy filled molecular orbital, its donor electrons. So that's what we're going to have here. So you can, again, you can show this two different ways. We'll show them both. So I will go from the electrons in this carbon-lithium bond, and then they're attacking pi star CO, which is bigger on carbon. Also, carbon has a delta plus, and opposites attract. Fill up pi star, you break pi. So this gives us this species. Okay. Oops. Nope. And so chlorine still has its lone pairs. Oxygen now has 3 lone pairs. So let's go through here. So the electrons from the pi bond are now a lone pair on oxygen, and I have too many different colors going on. All right, so the pi bond goes to oxygen, and then the electrons in the carbon-lithium bond, they formed, that bond between the methyl group and the carbonyl carbon. Super, so that's a nucleophilic addition, and we predicted it with FMOs. So let's think about how we can generalize this pattern, because, Cardi wants us to be able to recognize it, and we want to be able to recognize it too. Well, we're going to take a nucleophile, and it's going to add to a pi bond. And that pi bond in this case was our pi CO. So we had a nucleophile, and this time I'm going to do the abbreviation way. I'm just going to pretend like it's the carbon ion. It adds to a pi bond, and it makes a new sigma bond. And we break the pi CO. All right, so let's write all this down. So we're going to break pi CO because we filled pi star CO, and then we made a new sigma bond. Cool, so that's a nucleophilic addition. You add a nucleophile to a pi bond. If you guess that we're going to discuss the reverse of nucleophilic addition now, you're right. So let's take a look at this reaction. This is a slightly different molecule than we just looked at, and that's fine. And it can undergo a nucleophilic elimination. So let's think about what that might happen, how that might happen. So if a nucleophilic addition, a nucleophile adds and a pi bond is broken, in nucleophilic elimination, a pi bond is formed and a nucleophile is expelled, is eliminated. It's magic. Okay, so we have a nucleophile expelled. I like that better, or eliminated from the molecule. So you form that pi bond, and then these electrons go with hydroxide. All right, we broke this sigma bond. We should probably use a different color for that. It's a bit confusing. Okay, and so this is definitely, this nucleophilic elimination. It is definitely the reverse of the addition. So imagine we take these species and go in the other direction, which we can definitely do. I just want to rewrite it at the bottom so we don't confuse ourselves. So if I had asked you to analyze this reaction, I think you would correctly say that hydroxide is the nucleophile. It's going to use its non-bonding electrons to react with the electrophilic carbon. It's going to use its pi star CO orbital to accept the electrons. And we're going to have it attack carbon and push these electrons up on oxygen. And if we forget, oh, antibonding orbital, bigger on the less electronegative atom, that's cool. Just remember, partial positive on carbon, and opposites attract. All right, so we know nucleophilic addition, and we know nucleophilic elimination. So I want to make these molecules look exactly the same. All right, awesome. Okay. Now we have one more. If you're keeping track, there's 8 elementary steps. I know this is a super long video. I'm sorry for that. But we're going to look at this 8th elementary step, and it's called bimolecular elimination. So this one is going to be actually pretty hard to predict with FMOs. So I want you to I've given you the products. So now that I've given you the products, see if you can identify the nucleophile, electrophile, homolumos that are involved, and just at a minimum, provide a complete curved arrow mechanism. So I've done the initial analysis here, and I'm going to walk you through it. So there's a negative formal charge on hydroxide here. So this is electron rich and probably acting as a nucleophile. Now, technically, it's acting as a base, but base and nucleophiles are really similar, and we're going to talk more about that. It seems it's going to donate its non-bonding electrons. And you can see that those non-bonding electrons do end up becoming used to make a new sigma bond in the product. We can see that the CH bond here breaks and the CBr breaks. So if this is the electron-rich species, this must be the electron-poor species. And then thinking about, well, what is its acceptor orbital? Well, you need to think about what's going on. I mean, it's technically sigma star CH, but also sigma CBr breaks. So could it be sigma CBr? This is a tough one, like I said. So let's go ahead and see if we can just draw the curved arrows. We know that oxygen is making a bond to hydrogen because here it is in the product. So let's do that. So we are filling up sigma star CH. So we're breaking that sigma CH bond. Now where do those electrons go? Oh, they go here to make the new pi bond. So those electrons in the sigma CH, they're going to make this pi bond. So it makes the pi CC. And now when you make this pi CC, you're going to have 5 bonds to that carbon. Oh no. So instead, we break that CBr bond. So that does fill up sigma star. That does fill up sigma star CBr. And so that breaks the sigma CBr. And then those electrons end up as a new lone pair on bromide. Whew, that's a lot. Okay, so this reaction is an example of a bimolecular elimination step, an E2. So this E2 just means that the rate determining step involves 2 molecules. And we'll talk way more about this later. I don't want you to worry about it too much right now. Let's draw the mechanism one more time. So yes, hydroxide is kind of acting as a nucleophile, but it's really acting as a base. So E2 requires a strong base. It's attacking sigma star CH. Then the electrons in sigma CH, let's do this in a new color. The electrons in sigma CH, they come to form a new pi bond, and they're going to attack sigma star CBr. So sigma CH goes to sigma star CBr, and that breaks the carbon-bromine bond. So what you end up with, so you started out with a strong base, you started out with an alkyl halide or something with a leaving group, and we'll talk about this in so much detail later. For right now, just kind of follow along with the curved arrows and follow along with the FMO analysis. So it forms a leaving group and it forms an alkene. And then, of course, it forms the conjugate acid of the base, which in this case was hydroxide. So let's look at the FMOs here, because this is sort of important. And by sort of, I mean very. So here I'm drawing out sigma CH and sigma star CBr. So technically, this is our second. These are our purple steps. So I'm going to change that. All right, so this is our step 2. And we can look at step 1 too as well. Okay. So in step 1, you're just going to have your hydroxide lone pair. And it's not, okay, I'm saying step 1 and step 2. This is all happening at the same time. So really, I just mean that like arrow 1 and arrow 2. But at the same time, you have hydroxide attacking sigma star CX or CH. At the same time that's happening, you have the sigma CH breaking and those electrons reacting with sigma star CBr. And that's the part that I want to talk about here. So sigma CH, it must be aligned with sigma star CBr. They must be aligned like this. And this alignment is called anti-periplanar. So whatever sigma CH is reacting, it must be anti-periplanar to the carbon leaving group bond. And all that means, remember what anti means. So anti means that you have a 180-degree relationship between two things. So we have this 180-degree relationship between the sigma CH and the sigma CBr, sigma star CBr. So anti just means 180. And this is required because this is how the orbitals are nice and aligned. Orbitals must be aligned to overlap. Okay. I do want to talk about electron-rich and electron-poor species and think about why these steps occur. But let's just first kind of check in with our learning goals. So can we identify the HOMOs and LUMOs for a given molecule? Hopefully we can. That's when we talked about either the hard way or the easy way. So you could either draw out a complete reaction or complete MO diagram, or you could just use kind of your list of potential HOMOs and LUMOs that we generated on this page. Okay, so we can definitely achieve that learning goal. We can identify HOMOs and LUMOs for a given molecule. Predict whether or not a species will behave as an electrophile or a nucleophile. You're going to use your good HOMOs and LUMOs chart, right? So use your good HOMOs and LUMOs chart. I'm going to look for that for you, right? So we have our list of good HOMOs and LUMOs. Okay, so we can do that too. And then, yeah, we can do that too. And if we have a hard time with that, just think about electron-rich and electron-poor. So where you have lone pairs or you have negative charges. And electron-poor, you might have polar bonds. So think about electron-rich and electron-poor sites in molecules. Okay, can you predict products of single elementary steps using FMO theory? You can. And so the ones that I really showed you that you should definitely be able to do are that SN2, the coordination, and then I don't have them memorized, unfortunately. So not for heterolysis, but then for the fourth one, electrophilic addition, we predicted that one together. I would not expect you to be able to do the microscopic reverse to predict that. And then I would expect you to be able to do nucleophile addition, but not nucleophile elimination, and not the E2 that we just did. So it's just those four that I could ask you to predict the products using FMO theory for now. Eventually, all of them, but not yet. Okay, and then I want you to be able to draw the FMO interactions in these three steps. So the SN2, the coordination, and the nucleophile addition. Be able to draw those FMOs. And so it was the E2 we just did. It was hard, right? Some anti-periplanar, it was hard. Okay, draw the curved arrows for a predicted step. Yes, everyone can do that. And then identify these 8 elementary steps. So that's where I have the numbered slides where we've gone through and we have talked about the patterns. So just start to recognize the patterns. And it's going to take some practice, so we're just getting started on that. Okay. So I actually think that I'm going to end our discussion here. I do think that you should go back through these slides and list some electron-rich and electron-poor species. And I really want you to be thinking about functional groups and then patterns that you might observe in these molecules. And then finally, I'm going to address this in a different video, but then why do these steps occur? And you can be thinking about that on your own in the meantime. Okay, this is a lot. It's a lot of new ideas, and so you're just going to work through it slowly and practice.